Our second method to find the enthalpy of a reaction is called Hess's law. Basically, we are building thermochemical equations, so we are trying to find the enthalpy of a chemical equation, right? That makes it a thermochemical equation. Basically, what we do is building it up from different thermochemical equation, and then we can add up and find the enthalpy for our desired reaction. So I will explain more on this in the next slides. So you have to know some rules involving the delta H. Some of it we covered already when we were talking about thermochemical equations, and we're going over it again. And basically what we do in Hess's law is just like doing puzzles. If you like puzzles, you will like this method. I do like puzzles. I like this method. So it's just playing with different pieces of reactions as our pieces of puzzles, and then we add them together, we build our equation, and then we can find the enthalpy. You know that enthalpy is a state function, right? So it doesn't matter if we go from the reactants to the product in one-step reaction or in multi-steps reaction. So we can use that concept to find delta H. So before we move to that, let's talk about the rules on the delta H. So we already covered these two. You know that if you have a thermochemical equation, if you have a delta H, if you multiply any number to the coefficient of the chemical reaction, you do the same thing with a delta H. If you multiply the coefficient by 2, you multiply the delta H by 2. If you divide the coefficient by 2, you divide the delta H by 2. Okay, so any number that you're multiplying or dividing the coefficient, that will go on the delta H as well. The other thing, if you reverse the equation, you flip the equation, you change the sign of the delta H. So if an equation, for example, is exothermic, it's releasing heat, and you're flipping it, which means that it needs heat, so it's endothermic. So you just change the sign. So if A gives you B, and you have delta H equal A plus A, if you flip it and say B gives you A, now the delta H is negative A. You just change the sign. And the first example, if you have A gives you B, the delta H is plus A. If you multiply it by 2, so now you have 2A and 2B gives you plus 2A. Okay, if you do both of them at the same time, maybe you have to flip it and multiply it by 2. So for example, 2B gives you 2A, so delta H, it was plus, now it is negative, and it is multiplied by 2, so it's negative 2A. That's not that hard, right? So you just have to know the basic rules, and you can apply it and put your puzzle pieces together and find the delta H. So Hess's law, that's basically what Hess's law says. When reactants are converted to the products, the change in enthalpy is the same whether the reaction takes place in one step or in series of steps. So if you have, for example, you want to find what is the enthalpy when you go from A to B, and the delta H is unknown. If you have the delta H for A to C and C to D and D to F and then F to B, if you know the delta H of all these four, okay, so if you add all of these reactions together, so you know C with C, D with D, and F with F, what you have is going from A to B, okay. So if you add all of these delta H's, that would be the delta H of your A to B reaction, okay. That's because delta H is a state of function, right? So it doesn't matter what route you're taking to get to your final state, the difference is still the same. If you think about our initial example of a glass of water, if you have 12 ounces of water and you drink 6 ounces of it, you have 6 ounces of water. if you have 12 and you drink 1 and then 2 and then 3, again you have 6 ounces left. Okay, if you drink 8 ounces and you spit back 2, that would be gross, but still, just get the idea, right? So it doesn't matter how you get there, the difference is still the same. Okay, so delta H is the same thing, it's a state of function. So it doesn't matter what route you're taking, how many reactions you have until you get to your final state, the reactants, the product that you have in your desired reaction, it doesn't matter. So you built up those steps, then when you add the delta H, the delta H of your reactant is the same. So these concepts will be better understood if you do it on an example. Okay, so let's solve an example together. Okay, so we have these 3 thermochemical equations, and we want to calculate the enthalpy of this reaction. We have the enthalpy of the change in enthalpy of these 3 thermochemical reactions. Okay, so what we do in Hess's law, I told you, it's like a puzzle, right? And it's fun. Well, it's fun for me. I think it should be fun for you. So, and it's not hard. So you just have to learn the basic rules, and then you can set up your equations and find the enthalpy. So what you need to do is look at your desired reaction, like the reaction that you're trying to find the change in enthalpy, this one. Okay, so you go one by one of these elements, of these compounds that you have in your reaction, and check back in these top 3 reactions and see where you can find them. Okay, the first one is carbon, and the phase is GR, that stands for graphite. So carbon and graphite, where can you find C graphite in the top 3 reactions, 1, 2, or 3? So you see it in the first reaction. So then you have to adjust the reaction that you have here with the reaction that you're trying to find the enthalpy. So you have the graphite in the reactant side, and in reaction 1 it's also in the reactant side, so that's good, we don't need to flip it. If it was in the product, then we should flip it to put it in a place where the reaction that we're trying to find is. So it's in the reactant side, but you have 2 moles of carbon. Here we have 1 mole of carbon, but you need 2 moles of carbon. So the only thing you need to do is to multiply this by 2, the whole reaction. So when you multiply the reaction by 2, you also multiply the delta H by 2, the same number. Okay, so that's the first one. So let's write down the first one. So now I have 2C graphite plus 2O2 as gas gives me how many moles of CO2? 2 moles of CO2 in gas. And the delta H is what? Is 2 times negative 393.5 kilojoule. Okay. Okay. The second compound in the reaction is H2. And where do I find H2 in the top 3 reactions? The second one, I have H2, but I need 3 mole of H2. Here I have 1 mole. So what I need to do is to multiply it by 3, and that goes to the delta H as well. So you multiply delta H by 3. So I rewrite this equation here. So 3H2, and this was in the reactant side, and H2 in the reaction 2 is also in the reactant side, so there is no need to flip it. Okay, so 3H2 in gas phase plus, so we have 1 half times 3, so it's 3 halves O2 in gas phase will give you 3H2O liquid. Okay, and what is the delta H? It's 3 times negative 285.8 kilojoule. Okay, And the last one is C2H6 gas. Where do we find that? In the third reaction. But in the third reaction, it's in the reactant side, so I need it in the product side, so I have to flip it. And also, I have 2 moles of that, but I need only 1 mole, so you have to divide it by 2. So it's 1/2, and you have to flip it. Flip, okay? So if I flip it and divide it by 2, I would have 2, and it's not 4. So 2 CO2 in gas phase plus 3, not 6. I don't know why I say 3 but I write 6. Probably something wrong with me today. Okay, so 3 H2O in liquid phase. Don't forget the phases, always write a phase. And we flipped it, so that was the reactant now. So we go to the product, and C2H6 plus 7 divided by 2, it's 7/2 O2 in gas phase. Okay, and what happens to the delta H? Again, divided by 2 and change the sign. So it was a negative, now it's positive. 3119.6 kilojoule. Okay, so what you need to do in the end to make sure that you did the right thing is to add these 3 reactions. Okay, so the reactants and products that are the same can be cancelled out. So I have let's see, so I have 2 CO2 here, and I have 2 CO2, and why is it 4? It should be 2. Typo. So 2 CO2, so I can cancel out these 2. And so I have 3 water in liquid phase and 3 water in liquid phase. I have 2 O2 and 3 halves, which is 1.5, and this is 2, so it's 3.5. And here 7/2 is 3.5, so I can cancel out these with these 2. Okay, what I have left is the carbon, graphite, hydrogen, and this one. So if I rewrite this, I would write 2 carbon in graphite phase plus 3 H2 in gas phase. That's a reactant. In product, I have C2H6 in gas phase, and that's exactly what we want here to find the delta H. So if this is the same reaction that we want, what you need to do to find the enthalpy, you just add these together, and you have to be careful. These 2 are negative and this is positive when you're adding it. So when you add all of these together, the delta H of the reaction is negative 84.6 kilojoule. So it was fun, wasn't it? So you have to just make your pieces of puzzles, go for the compound, see what changes it needs to make it in the form and number of moles that you need in your reactant, and then add all of them together, see if you put all the pieces of puzzles together right. So you add the reaction together to see if you get back the reaction that you want. If it's the same thing, then you just add the delta H's, and that will be the change in enthalpy of your reaction. So now I want you to go ahead and find the delta H of reaction for this reaction here by using these 2 reactions. Okay, you have the delta H of these 2 reactions, and you're trying to find this. change the necessary, you apply the necessary changes and find delta H of the reaction. Okay, so the first compound, CaO, where do you find it? CaO, we have it in the second reaction, and it's in the product side. We need it in the reactant side, and we have 2 moles of that. We need 1, so you flip it, and also you have to multiply it by 1/2. Okay, CO2 is in the first reaction, and it's in the reactant side, and it's just 1 mole, so that's fine. And CaCO3 also in the first one, and the product side, and 1 mole, so that's fine. So we don't touch the first one, we just flip and divide it by 2 for the second one. Okay, so I rewrite these 2 equations. So I have calcium, I do not touch the first one, just keep it as it is. 1/2 of oxygen gram gives you CaCO3 solid, and the delta H is negative 812.8 kilojoule. Okay, the second one we have to flip it and divide it by 2, so it's CaO solid, and that's the only reactant because that's the only product. And you have Ca solid plus 1/2, we divide all of them by 2, right? 1/2 of oxygen in gas phase. Okay, and the delta H is, let me write the delta H, not there because we don't have enough space. So the delta H is 1/2 times, we change the sign because we flip it, so it's negative, and we have to make it positive. Positive 1269.8 kilojoules. Okay, so so we have to add these 2 reactions to make sure that we have the right reaction. So we have calcium solid, we have 1/2 oxygen and 1/2 oxygen on the reactant side and product side, and that's it. So we have a CaO solid, so we have this, and we have this one, plus CO2 gas gives you CaCO3 solid, and that's exactly the reaction that we want. So we just add these 2, and the delta H of the reaction is negative 177.9 kilojoule. Therefore it's option C. So Hess's law is fun, I guess. So you just have to know, it's simple, when you flip it, change the sign. If you multiply it or divide it by anything, do the same thing with the delta H. Then put these things together and find delta H. So it's just like working with puzzles.